All right, so we have some data. Let's continue. And next part we're going to do is figure out what are the cruise conditions based on our cruising speed and our cruise altitude. First thing we need to do is figure out what our cruise speed would be in feet per second, and that'd be our true airspeed. We're given our Mach airspeed, so if we find the speed of sound at an altitude of 20,000 feet, which is going to be a function of the atmospheric temperature at the altitude, we'll just assume a standard day. Then we can figure out what our actual true airspeed will be at that Mach 0.6, which we need for determining our weight fraction for our cruise. So let's continue with that. If we want to add a loiter segment later, if we want to change our mission, it might be useful to know. So we can figure out our temperature at our cruise altitude using our temperature ratio. Temperature ratio for the standard atmosphere model, the US standard atmosphere, is defined by this equation here. So temperature ratio is the temperature at altitude divided by temperature at sea level, or reference temperature, which is 519 Rankine. It's an absolute temperature scale. So if you're using the British units, then the reference temperature is 519 Rankine, roughly. And the lapse rate, which is this term here, is the rate of decrease in the atmospheric temperature as a function of the altitude h, and h is in feet. So what we can do is I can say that if I want to find our actual temperature, I just multiply the reference temperature by this temperature ratio theta. So I would get the reference temperature times this quantity here, 1 minus 0.50, and then 68756 times our altitude in feet, 20,000, close bracket. So our outside air temperature at cruise is 447.63, and that is the same units of Rankine. So the next thing we need to do is we need to figure out the speed of sound. The speed of sound can be approximated or is calculated as the square root of your ratio of specific heats, gamma, times, so let me double check a number, the ratio of specific heats times your gas constant, and that'd be units of pounds per slug per degree Rankine, times your outside air temperature. So we can put that in here as speed of sound, and it's going to give us units of feet per second. So this is equal to the square root. The specific heats, or the ratio of specific heats for air, is 1.4. I'm going to multiply that by our specific gas constant for air, which is 1716. That's units of foot-pound per slug per Rankine, times the outside air temperature. If we multiply out those units, we'd end up with feet per second. So the speed of sound at that altitude, just over 1,000 feet per second. So then how do we convert our Mach speed to our true airspeed? So true airspeed is simply going to be equal to the speed of sound times our Mach number. Our Mach number is just the percentage of the speed of sound that we're traveling at. So 60% of this 1037 is our true airspeed. We're traveling at 622 feet per second. So we have some information for our cruise data. We have our cruise altitude. We have our specific fuel consumption in the correct units. We have a prop efficiency. The next thing I added here was an estimation for our maximum lift-to-drag ratio. Now, if we assume a simplified drag model, maybe I can write that up here, simplified drag model, then we can approximate the maximum lift-to-drag ratio as 1/2 times the square root of this parameter here, pi times our aspect ratio of our main wing, times this E term is our span efficiency, or Oswald span efficiency. I've just approximated that as 0.75 for now. We can calculate that more accurately later on. and divided by our minimum drag, or CD naught. In the simplified drag model, the minimum drag is the same thing as our zero lift drag. It is just the intercept of our drag polar curve with the zero lift axis. So for modern aircraft, this can range between 0.02, 0.03, 0.04 would be maybe a higher drag, maybe a pontoon aircraft or an aircraft that's not so aerodynamically refined. A turboprop regional carrier has probably got some pretty good drag refinement or drag reduction. So I'm just going to put in this value for now, and later on I'll make sure that I would do a better analysis to get a more accurate number. For now, we just want a number so that we can continue on and get some initial estimations and understand just the process of doing our sizing. So we're ready now to go and do our weight estimation for the cruise weight fraction. And for cruise, for a propeller aircraft, if we rearrange the Breguet range equation, we get this form of an equation where the weight fraction for our cruise segment is equal to the exponential of the ratio -r, our range, times our SFC on a horsepower basis, divided by 550 times our propeller efficiency times our lift to drag ratio during our cruise. And for a propeller aircraft, we'll find out later that the cruise, the optimal lift to drag ratio to fly at for the cruise to optimize range would be our maximum lift to drag ratio. So if we calculate our lift to drag ratio, maybe I can add a column here. I'll move this stuff up and I'll calculate my L over D max. And this is going to be equal to 0.5 times the square root of pi times my aspect ratio times my span efficiency divided by my minimum drag. So I get a maximum lift to drag ratio for an aspect ratio wing of about 8 and a minimum drag of 0.3 of around 12.5. So a realistic number, perhaps. So I'm going to use that in this relationship here. Notice if my cruise mission specifies a range, I don't actually need to know my cruising speed for a propeller aircraft. That would be not the case for a jet-powered aircraft, but in this case, it is only a function of our lift-to-drag ratio and our specific fuel consumption. So it would still be a function of our velocity through the lift-to-drag ratio, but doesn't appear directly in the equation here. So let's plug in this relationship. Is equal to the exponential. Now here is where the units really matter, and I'll show what would happen if we use the wrong units. So our range, 1.2 million feet, times our specific fuel consumption, divided by 550, divided by our prop efficiency, and then finally divided by our lift-to-drag ratio. And we get a cruise segment of 0.972. Now this seems strangely high. I would imagine, I can see the issue here. I have a cruise range of 200 nautical miles. That's not very far. I think in my original I had planned to write to 2,000. Not much better. So we get 2,000 nautical miles. We can see that that number decreases quite a bit. So what I see often as a mistake is in this cruise, we forget to convert our specific horsepower on a per second basis. So if we do that, you might get an answer that looks quite small. In this case, it's so small it's 0. So what looks realistic is if you also make the mistake of using nautical miles. So now this number looks more realistic, 0.843, but it is incorrect. If you do unit analysis, you'll find out that the units are inconsistent. So it is really important to make sure that you're working with consistent units, which means converting your cruise range to the base units of feet and converting your specific fuel consumption to the base units of per second, not per hour. So if we do that, We still get a realistic number, but this is a correct number based on these approximate values for our cruise segment. So then our total, I'll write it up here and save some space. Our total is simply the multiplication of all of these values. So I'm just going to do equals product of these values, just multiply them all together, and I get 0.709. So let me write total here instead. So this is our total mission weight fraction. So at the end of the mission that we've designed, which is just a simple cruise mission with a range of 2,000 nautical miles, our aircraft will weigh about 70% of its initial gross takeoff weight. So how do we determine what our fuel weight is from that? Well, if only our fuel weight is being burned, then our fuel fraction is simply going to be 1 minus our mission weight fraction. So we get our fuel fraction then of 0.291. So about 30% of our aircraft weight is going to be fuel, which makes sense. We lose 30% of our weight, and that 30% is fuel. So that becomes our fuel fraction.